All right, welcome everybody. Thank you so much for coming. It's great to have such a full house tonight. We're really excited. I will just make a few brief announcements because I know you actually came to hear somebody other than me tonight. But I will tell you that we do lots of great programs here at MoMath. Some of you have been here before, but others of you, maybe this is your first time. I hope you'll sign up to be on our mailing list so you can see all the other wonderful programs we do and that we'll see you back here again. In particular, I'll just call out one very exciting program happening this Sunday. We have a visiting mathematician, a distinguished visiting mathematician from Dartmouth, who gave a whole puzzle mini course earlier this year, and he's going to reprise that in one day. So if you missed the puzzle mini course and you want to get a taste of how great it was, you can still sign up and come join us on Sunday for a day of puzzles with Peter Winkler, who happens to be right here. I'll also mention to you that Pi Day falls on a weekend this year, and that means there's going to be a lot of cool stuff going on here. So come on Saturday, March 14th, if you want to celebrate Pi Day with us. I'm really delighted that we've had this partnership with NYU, and in particular with Dr. Moira Dillon, who reached out to us here at the museum probably a couple of years ago at this point and said, wouldn't it be great if we could work together? I study how cognition works, how people learn, in particular how spatial relationships are developing in children versus adults. That sounded great to us, and as a result of her hard work in building up a program, we now get to bring you a wonderful speaker tonight. So I'm going to turn it over to Dr. Dillon, who will introduce the rest of the evening. Please join me in welcoming and thanking Dr. Moira Dillon.
Hello, everyone. My name's Moira Dillon, and I'm an assistant professor of psychology at New York University. I'm also the director of the Lab for the Developing Mind at NYU. My lab has been partnering with MoMath, as Sydney mentioned, for about 2.5 years to conduct some studies here in the museum. Maybe some of you have participated, or maybe your children have, looking at how mathematical concepts develop in the mind. We're also collaborating on some new programming at the intersection of psychology and mathematics. And that brings us to tonight's talk series, Minds on Math. Through 2024, Minds on Math, co-sponsored by my lab and by the museum and supported by the National Science Foundation, it will feature accomplished scholars in developmental psychology, cognitive science, mathematics, and education, who conduct research on how our minds and brains learn and appreciate math and related fields. This evening, I'm very happy to introduce Dr. Joshua Tenenbaum as our Minds on Math speaker. Currently a professor of brain and cognitive sciences at MIT, Josh is also a principal investigator of the Computer Science and Artificial Intelligence Lab at MIT, and a research leader in the Center for Brains, Minds, and Machines at MIT. Josh's work focuses on how we humans, with our natural intelligence, are able to harness the limited and noisy experiences of everyday life to learn, reason, and think in ways that exceed the learning, reasoning, and thinking of any artificial intelligence. Josh's work merges computational cognitive science and experimental psychology, allowing them to inform one another. By building computational models of human intelligence, his work promises to create AI that better understands us and that we can better understand. Josh has received prestigious accolades for his work, too numerous to list here, but I note in particular that he's the recipient of the 2019 MacArthur Foundation Fellowship, also known as the MacArthur Genius Award. In our field, Josh is indeed recognized as a genius, but Josh is also recognized as a communicator, a teacher, and a mentor. It makes sense that Josh is one of the world's leading experts on learning, given how passionate he is both as a learner and as a facilitator of others' learning. Tonight, this is why I'm particularly pleased to have him here, sharing with us both his work and also his passion for that work. I look forward to learning a great deal. Please join me in welcoming Josh.
Thank you. Thanks so much. Let me move this away. Can everybody hear me okay? All right. Thanks so much, Molly, for that wonderful introduction, for the invitation, and for the museum for hosting this event. It's a great pleasure to be here. I've heard of the museum. This is my first time walking in through the doors, but I've heard of the museum since it was starting to be set up, and I've long wanted to visit, so this is a great opportunity, and I'm very excited to also tell you about the work that we've been doing. So as Molly said, the work that we are doing really sits between a number of fields. Not really mathematics, but you'll see that there are important, I think, mathematical ideas in the work that we're doing, and even connections to the origins of mathematics in the developing human mind as well as where mathematical ideas and related ideas in physics come from originally, where science starts. But most of what we're about here is trying to understand the origin, the nature of human intelligence in the mind and brain in engineering terms. We like to talk about reverse engineering the mind, and that means studying the basic science of how intelligence arises in the mind and brain, but approaching it like engineers. So using various mathematical toolkits that come from engineering to build models that we can test in experiments. But just as important is the proof of concept and the practical application that comes when you take those ideas and you actually do real engineering with them, when you try to build more human-like forms of artificial intelligence. As Molly said, machines, she said it beautifully, machine systems that can better understand us, that we can better understand, and by building them, allow us to, in turn, better understand ourselves. Now, it's an extremely exciting time to be working at the interface of human cognitive science and AI, because while these fields grew up together, starting in the 1950s, they've often spent most of their time growing apart, and occasionally coming back together, and then growing apart again. And this is one of these exciting moments of reconvergence. Okay? But I think, as you'll see, it's the gaps between human and artificial intelligence that really drive our work. Because I think, well, we would all agree, everyone knows that artificial intelligence is here in a big way these days and increasingly having an impact in our lives. I think it's fair to say that today's AI technologies are far from anything we would call real AI, that the founders of the field would have called AI. That is, we have machines that do things that we used to think only humans could do. That's what I mean by an AI technology. Okay? But we have nothing like the flexible, general-purpose, common-sense intelligence that each and every one of you uses to do every one of these things for yourselves, without having to be built by a dedicated team of highly paid engineers, trained on massive amounts of data, in a very domain and task-specific way. Every one of these systems, whether it's self-driving cars or machines that play Go or speech recognition or chess players or Jeopardy players and so on, each of these systems just does that one thing. But you do each and every one of these things for yourself. So I'd like to understand, and my research is motivated by trying to understand what's the difference and how can we understand it in engineering terms. Now, there's many gaps, but I think the easiest to appreciate, and the fundamental one that drives a lot of what I'm going to be talking about today, is this: that at the heart of today's AI technologies are recent, and I would say not just recent, but a long history of breakthroughs in pattern recognition and function approximation, machine learning, data science, deep learning. Probably many of you have heard of these things, and probably many of you work in these areas, in fact, okay, or use these tools in your own work. Okay. And it's undeniable that we've made great strides over decades, and especially recently, in finding patterns in data. But intelligence goes so far beyond that, not just recognizing patterns, but all the activities that I like to call modeling the world. Okay? And to make a nod to mathematics, right? Mathematics is a way of modeling the world. We have other ways of modeling the world in physics and other sciences. Okay? Some of our models we express in words, but this is so much at the heart of human intelligence. So think about all the ways our minds don't just find patterns in what we see, but explain and understand. Or our ability not just to recognize familiar things, but to imagine new things, maybe things that we've never seen or that nobody's ever seen. Then to make plans and solve problems to make those things real. And learning as building new models of the world as you experience more or find gaps in your current models. If you'd like to read more about this perspective, there's a very long, but hopefully rewarding paper by Brendan Lake and colleagues, including myself, that you can download for free on Archive, Building Machines That Learn and Think Like People. That is a sort of a good introduction to the ideas that we're talking about here. Okay. Now, I think it's fair to say that we are far from being able to explain these sorts of things. None of our machines do anything remotely like this at this point. Okay? We are far from having the ability to build machines that can model the world at even the level of a 1.5-year-old child, okay? Maybe even a 3-month-old. But imagine if we could. Imagine if we could build a machine that grows into intelligence the way a person does, that starts like a baby and learns like a child. Even if this is far, far away from where we are right now, think about what small steps towards this goal could be. These are pictures of my own child who's just turned 18. And we all know as a parent the remarkable experience of seeing somebody grow into intelligence. Okay? we are very far from being able to have machines that could do that, but even small steps towards a machine that could learn like this would be big. Even small steps could change the world. Today's machine learning, like deep learning or reinforcement learning, if you've heard of these ideas, were based on simple small steps towards models of very much simpler kinds of animal learning processes published in the 1950s, 60s, and 70s. Think like Pavlov's dogs or a rat in a maze, okay? And those technologies, when scaled up, see how much they've changed the world. So think about what we could do if we could take the next small step with actual human learning, okay? Now, this is not a new idea for me. It's one of the oldest ideas in AI. It may be the oldest and maybe the best idea. It goes back in some form to this paper published in 1950 by Alan Turing, even older than the papers behind today's, let's say, deep learning technologies. This paper is most famous for introducing the idea of intelligence as computation and the famous Turing test, right? But in a lesser known part of the paper, Alan Turing sketched out what it might take to build a machine that could be intelligent, that could pass the Turing test. And he frankly admitted he had no idea. But he figured the best route, instead of trying to build a machine with the intelligence of an adult, would be to try to build a child machine that starts like a child and learns like a child, because presumably that would be simpler. To pick out a key quote here, he says, presumably the child's brain is simpler than the adult's. Maybe it's something like a notebook as one buys it from the stationers. Rather little mechanism and lots of blank sheets. Okay. Well, Turing was brilliant, and he was also wise, so he included the word presumably. He knew that he was just making a presumption. And one of the things that we've learned from the last couple of decades of human cognitive science research is that Turing, while brilliant about many things, including mathematics, was wrong about this. That in many ways, children's starting state is far more than just a notebook of blank sheets, and learning is much more than just copying down what somebody writes on the blackboard. In many ways, this is where our research starts. In the slightly more technical terms, we talk about what is the starting state of the mind, or the inductive bias, and what are the learning procedures. And due to work by many people, here I'm highlighting a number of my colleagues in developmental psychology, like Liz Spelke, who talked earlier in this series. Some of you might have seen her. Rebecca Sachs, Alison Gopnik, Laura Schultz. These and many others have studied all the ways in which children start off with much more in them, and they learn in much more sophisticated ways. So you might have heard a phrase like core cognition, that's Spelke's phrase, talking about the very basic common sense that's built into the brain and minds of infants. Or the child as scientist that Alison Gopnik has made popular, okay, and really developed in quite deep ways. The idea that children's learning is kind of like forming theories and doing informal experiments. Just like a scientist playing around in the lab, a child playing around in the crib might be actually making fundamental discoveries. Okay. What I'm going to talk about here are ways to use engineering terms to kind of extend, elaborate, and go beyond some of those ideas. So you'll hear about phrases like the game engine in your head or the child as coder. Okay. These are ways to use engineering tools to capture and extend some of these insights. And we're focusing on basic aspects of common sense that you can see in any 1.5-year-old, but no machine. So we talk about intuitive physics and intuitive psychology. And just to illustrate, by intuitive physics, I mean the kind of intelligence that you see in this kid over here, this 1.5-year-old, or any kid at home, playing with blocks, or here stacking up cups. And think about what has to go on inside his head to make the plans and execute them that he's doing right here. He stacked up 3 cups, and now he has the idea to build a taller stack by making a smaller stack of 2 and then putting it on the stack of 3. Of course, some problems come up along the way. And so think about what he has to do to debug that plan. Okay? It's cute, it's sweet, but it's also incredibly intelligent. We have robots that can manipulate objects in the world. Okay? And we will someday have robots that maybe can do something like this, but we are incredibly far from that kind of common sense physical intelligence. Or think about, on intuitive psychology, this video here that is from a famous set of experiments by Felix Warneken and Michael Tomasello. There's a little bit of sound. If you can't hear it, don't worry about it. The subject in this experiment is that 1.5-year-old there in the back. He, like you, is watching somebody do something a little bit odd. It's something he's never seen before, but he can figure out what the person is doing and even how to help them. Yeah. Again, incredibly cute and sweet, but also incredibly intelligent. again, what has to be going on inside his minds to analyze this action, to understand the person's goals when they're engaging in the physical world in a somewhat unusual way, right? And then figure out how to help him. Maybe the best part is what's going to happen right after he opens the door. Watch as he looks up, kind of makes eye contact, and then looks right down at the guy's hands. It's almost as if, and in fact, I think it's not just as if, it is, making eye contact, trying to register a social signal. Did I understand your goal? Did I do the right thing? And if so, I can predict that you're going to take those books and put them on there, so I'm looking down at your hands holding the books to see if you do what I think you're going to do. So what we try to do in our work is to build mathematical models of the mental models inside these kids' heads. So I'm sketching here with these diagrams what we think of as the intuitive physics models inside these kids' heads, or this model here, which is a mental model of how people act, right? It's not a model of how people act, it's a model of how people model how people act. I know you can handle a little bit of recursion. So by intuitive physics, we mean what is our mental model of the state of the world, the physical objects that evolves over time, and that gives rise to the images we see, so that we can work backwards from perceiving the world to the underlying physics. Or here we add on to that the idea of a planning agent. An agent has a goal. Maybe his goal is to get the books inside the cabinet. He makes plans to achieve his goal subject to his beliefs, which are in turn formed by his perception of the state of the world, informed by where he is. And by seeing somebody's actions in a certain state, we can work backwards and make inferences about what they want and what they think. Even a young child can do that kind of thing. So our job is to put the math on these pictures, okay? To write down their equations, and then use those both as models of how kids and adults think, and how to put these kinds of capacities into machines. Imagine if we could have robots that could help out around the house like that kid. Again, it would be amazing. All right. So what kind of math do we need to capture these models? Well, one of the things that's most exciting to me right now, and there's many reasons why this idea that started with Turing and has gone through many generations. Why is it time to make progress on this when we haven't really executed on this vision before? The most important is the work of the developmental psychologists I've been talking about, who have showed us all the ways that kids' minds are built with so much and learn in so much smarter ways than computer scientists might have supposed. But there are also advances in computer science and mathematics where we've been able now to look back at multiple waves of AI and identify a number of good ideas that people used to think were mutually exclusive. And now we realize, well, actually, they're all important, and even better, we're starting to understand how to put them together. So there's three big ideas about how to think about intelligence in computational terms that each kind of have a corresponding different branch of mathematics, interestingly. And they've each had their days in the sun, their rises and falls in the history of AI. But what I think we've learned is that we need all of them, and we need tools for putting them together. So the first big idea is the idea of intelligence as symbol manipulation. This is the oldest, and I would argue the best, idea about how to think about intelligence in engineering or mathematical terms. It goes back in some ways to Aristotle, at least in the Western tradition. Aristotle introduced formal logic in the form of a syllogism or a formal algebraic-like structure for thought. You're familiar with this with examples like Socrates is a man, all men are mortal, therefore Socrates is mortal. And Aristotle said, well, you can make that argument, but it's really an instance of a more general formula that, at least in my translation, was written as something like alpha is a beta, all beta are gamma, therefore alpha is a gamma. Okay. In that hybrid of English and Greek. Okay. But the point is, he introduced variables that could stand for anything. And that was one of the first instances we know of symbolic computation. And then there's many other contributors to this tradition: Boole, Turing, Alonzo Church, John McCarthy, the inventor of the Lisp language. I'm just curious here, I know this is a very sophisticated audience. How many people are familiar with Lisp? Okay, great, wonderful. How many people are allergic to Lisp? I love Lisp, and you'll see a little bit of it at the end. Okay. Lisp is a computer programming language that was popular in the early days of AI and never really went away, but it embodies in an elegant way the mathematics of the lambda calculus, which was introduced by Alonzo Church, and it's sort of a software-level abstraction of the Turing machine, which was Alan Turing's way of formalizing universal computation. It's a universal programming language that has many appealing properties, not only because of how it can express rules, but how it can express rules about rules or reasoning about rules. Okay. And in the early days of AI, people would write down all sorts of if-then rules in Lisp. Like, for example, if you see an animal and it wags its tail and barks, then it's a dog. Or if it has whiskers and meows, then it's a cat. Or these days, if you wanted to build a self-driving car, you might write down rules like, if you see a red light, stop. Otherwise, if it's green, go. Okay. Now, we can already see what the problems are. There's exceptions that might not be covered, or you don't want your car to just go when the light turns green. What if there's a person there? Not everybody follows the rules, or another car. So you have to have all sorts of exceptions, right? Like, well, if it's green, then go, unless there's a person, or unless there's another car, or unless there's an elephant, or unless there's, and it goes on and on and on. And while people made a lot of progress writing down rules for intelligence in symbolic programming languages, the broad consensus was that that wasn't going to be sufficient. And there were many different things that were proposed to try to move beyond that, but certainly one idea which had an early phase of importance in the 1960s and then again in the 1980s and is now back in a big way is the notion of neural networks as a very general toolkit inspired by basic abstractions of how neurons in the cortex seem to work. A simple computing element that takes a number of inputs, weights them in some ways, sums up the weighted contributions of those inputs, and then if the sum exceeds some threshold, makes a spike or fires more or less. Okay? And the idea of neural networks is that you take that basic element, you make a number of those processors, you scale them up into bigger and deeper multi-layered systems. Here are several famous examples of what are called deep convolutional neural networks. Okay? The LaNet or the AlexNet, this one over here on the lower right. And these are the tools that have been most, especially in the last few years, turned into practical, say, computer vision systems by companies like Google, Facebook, many others. Okay? These, in very exciting work by some neuroscientists, including some of my colleagues at MIT, like Jim DiCarlo, these ideas which were originally inspired by studying vision in the brain, okay, and then turned into these very powerful engineering tools, are now back and have provided some of the best actual computational models of how multiple levels of neural processing in the primate brain work. But that's another story that I'm not going to go into here. Okay. It's just a very exciting set of developments. It is very complementary to the idea of intelligence as symbol processing, because these are systems where you don't tell them what rules to follow, but rather you lay out the overall architecture, and then you have thousands or millions or even billions of numerical parameters, the weights on these neural networks, which can be tuned to optimize some score or loss function on data. And the key thing behind them is that the entire system is what's called end-to-end differentiable. So while the math of sorry, I don't want to go back there. While the math of the previous slide was essentially algebra and logic, here the basic math is calculus, right? These are systems which have an incredibly large number of degrees of freedom, but you write down a cost function or a loss function, a measure of how good or badly the system is doing on fitting some training data set. And then you can optimize that cost function by computing the derivatives of the error function for each of the weights, and then do what's called gradient descent, an idea that goes back to Newton, like other things in calculus. It just says follow the direction of steepest descent to minimize error. And you can do that in parallel on all the billions of parameters in these networks. Okay. Interestingly, the way you're able to do that is by using symbolic computation. If you're familiar with languages like TensorFlow or PyTorch, the thing that makes these networks work in engineering practice is higher order functional programs like autograd or automatic differentiation. The idea is you write these networks as a big program, and then you have another program which computes the derivative of the first program, and that allows you to do gradient descent on these really complex systems. in ways that no individual person understands. So even today's neural networks are really interesting hybrids of this kind of picture of intelligence and the symbolic computation picture. Now there's a third, which was coming into its peak when I was in grad school, and as anyone who's an academic or researcher knows, that those ideas have a particularly outsized influence on developing researchers, and has also had its different moments in the sun, which is the idea of intelligence as probabilistic inference or Bayesian inference, and it's deeply related to the idea of causal inference. But here the idea is using the math of yet a third branch of mathematics, probability theory, to capture motifs and scale them up for not just seeing patterns in data, but for inferring the underlying causes. Like, for example, in that Bayesian network over there in the upper left, the famous QMR network, which has nodes for diseases and symptoms, and that can be used to observe a sparse pattern of symptoms or effects and reason backwards to the most likely underlying causes, a pattern of one or more diseases that best explains those symptoms. Okay? And it's an implementation of Bayes' rule, which again, I'm sure many people here are familiar with. Okay? Bayesian networks are very similar to neural networks, but the arrows go in a different direction. That's the main difference. In a neural network, the arrows go up. In a Bayesian network, the arrows go down. Or maybe it's left or right. And that's sort of glib, but there's a fundamental difference, which is that in the neural network, the arrows represent the flow of information from inputs, like information coming into your eyes, and the output is some behavior. Whereas in a Bayesian network or a causal network, they go from causes to effects. And information can go that way if you're predicting, well, if you have this disease, here's the symptom I expect. But information can also flow against the arrows when you do inference, right? When you see the effects and have to reason backwards to the underlying causes. And the tools of probabilistic inference in Bayesian networks are tools that allow you in a very scalable, general purpose way to go both with and against the direction of causality. And you put all these things together, and we think you have a key set of building blocks for engineering and reverse engineering intelligence. Now, different people do this in different ways, but in our group and some of our colleagues, we like to talk about what we call probabilistic programs, which, kind of like neural networks, they started originally as ways of sort of generalizing those ideas of Bayesian networks and probabilistic inference that I just talked about. But really, at this point, probabilistic programming languages are very general sets of tools that allow us to combine all of these features. Symbol manipulation for abstract knowledge representation and reasoning, probabilistic inference on causal models for reasoning backwards to causes from sparse patterns of uncertain effects, and neural networks for pattern recognition and function approximation. And we think you need to put all of these together in order to start to make progress on the hard problems of how we, even young children, learn to model the world. If you'd like to learn more about probabilistic programming, I'm highlighting a number of probabilistic programming languages. The ones in bold, like Pyro or Gen, these are, or TensorFlow probability, these are languages that were developed in various companies and also academic labs. Gen is from MIT, Pyro is from Uber AI, TensorFlow probability was developed inside Google. And they all sit on top of modern languages for deep learning like TensorFlow and PyTorch, the languages developed in these big companies for the neural network pattern recognition pipeline. But they add these other capacities on top. And if you'd like a little sort of intro informal textbook that self-paces you through learning about probabilistic programs, the probmods.org webbook is a great place to look for that. Now, there's one more technical idea, which is orthogonal to the idea of probabilistic programs, and this is like what programs we actually want to use. The slogan here that I like to use is the game engine in the head. So again, I think probably many of you are familiar with game engines. Probably many of you are familiar with video games, or game engines as the tools that are used to design the rich, immersive, interactive experiences as players explore virtual worlds that don't exist in the real world, or maybe are remote, like a space station, or the Wild West, or some alien civilization, or some undersea caves. Okay, but the ability for a game designer to create some new experience and make it real for a player. How does that work? Well, these are tools that allow game designers to do that without having to write all of computer graphics or physical simulation from scratch. But they capture just enough of the way light bounces off the surfaces of objects to render in real time, or often much faster than real time, what the world looks like in any number of different situations that you can imagine. And they also capture very fast approximations to physics, like let's say Newtonian physics. They use some actual force mechanics, but they also use all sorts of physics engine hacks that allow them to simulate very complex physical interactions again, in real time or faster than real time as a player interacts with the world. And it's not exactly the way a physicist would do it. In fact, it might be very different. But it just has to look good and respond in natural ways. So we think that this toolkit is a good first approximation, surely wrong in many ways, but a good first approximation to some of that basic common sense core knowledge, let's say, about physics, that researchers like Liz Spelke have shown might be built into our brains in some form from birth. Okay? And the idea is to wrap these game engine programs inside probabilistic programming languages so that we can do inference, so that we can go forwards and backwards, so that we can make good guesses about their latent parameters. That means like see an object interacting and make a guess at how much it weighs, for example. Use that as our framework for common sense inference. Now, if you have followed recent machine learning, there's a lot of work right now that uses game engines in order to generate training data for, say, neural network or machine learning systems. Okay. And then people talk about sim to real, which is our systems have to transfer from the simulated world to the real world. What we're talking about is crucially different, which is what summed up by the game engine in the head. The key idea here is the game engine isn't the training ground for the AI, it's actually the mental model, right? So when a kid looks at, say, this stack of wooden blocks and a toy on top of it and imagines what happens if I roll this ball, right? The ability to imagine ways in which he might knock over the stack of blocks and cause the thing on top to fall over, that's a simulation that he runs in his head using these game engine tools. Okay. Here's an example of a game engine simulator called 3D World, which was developed as a collaboration between MIT and IBM researchers. And it's just one way to use tools. It sits on top of Unity, if you know that. And it allows us to imagine many different objects and natural scenes to simulate physical interactions between rigid bodies, collisions, knocking things over, more complicated Rube Goldberg type machines, all sorts of things you might play around the house. And again, think of your kids or think of when you were a kid setting these things up and what has to go on in your head to imagine what might happen next. Soft bodies, cloth, solids interacting with water, and so on. Okay. So these are some of the tools that we use, and we put them together to build models of what goes on in your mind when you, for example, make physical judgments. So now I'm going to shift to showing you some of the kinds of experiments that we do, how we test these models. So, for example, to study intuitive physics, we might give people scenes of these stacks of blocks or towers and ask them to make a judgment, for example, about how stable they are. How likely are they to fall under gravity? Think of this as a freeze frame of a movie. Hopefully you'll all agree that the scenes in the upper left look like they're pretty stable, right? Whereas the scenes in the lower right look like they should be falling if I turn on the movie or turn on gravity. Okay. So how do we capture that? That is, in fact, what people judge. Okay. Well, we're going to fit a model like this where the first step is you have to understand how you work backwards from an image to something like the physical state of the world, the kind of thing that you can do dynamics calculations on. And this is what we call a kind of inverse graphics, right? Graphics, computer graphics, is the process of going from a description of the three-dimensional world to a 2D image when you shine light on it. And vision, perception, is going the other direction. So we see, for example, an image of a stack of blocks here, and we want to work backwards to the underlying world state. Now you look at this and you might say, well, these two images look pretty similar except that one's in color and the other's in black and white. I just color them differently just to mark the difference. But the key way that you know that the percept, the output of the inverse graphics, are inverting that rendering engine, which we do using a kind of Bayesian inference in our probabilistic programming language. I'll show you a little bit more what that means in a second. But the way we do that, or I'll show you a little more in a second how we do that, but what we do is we produce in this case, this is a single Bayesian posterior sample, a single hypothesis of the 3D structure of blocks that could have produced that image. That's the causes for the bottom effect, okay? And that's one hypothesis. Here's another one, here's another one. I'll go back and forth between them a few times. Hopefully you can see the blocks kind of moving around in 3D, okay? So each of those hypotheses, I mean, I have to render them in 2D here, but they're actually 3D objects, and what you're seeing is a little bit of posterior uncertainty. I'm not exactly sure where the blocks are. I can't perfectly localize them. That uncertainty turns out to be important. It's the beginnings of the probabilistic inference. Here's another scene. Again, this is one, if you can see down there. Sorry for those in the back who can't see it, but this is another stack of blocks, a kind of a guess if you turn around, or maybe you can see it on the side or the screen in the back if you can't see the things on the bottom here. Here's what that looks like. And again, you can see these objects moving around a little bit, representing some uncertainty about where the blocks are. Now, how do we get these samples? Well, one way to get them is to do something called MCMC, or Markov chain Monte Carlo. For those of you in data science or statistics, you might be familiar with this. These are what are sometimes called top-down ways of doing Bayesian inference in complex probabilistic models, where we make a hypothesis, we see how well it fits the data, and then we adjust. And we take a series of small steps. They are stochastic steps. It's a Markov chain, if you know that idea from probability theory. A biased random walk. And if you're willing to wait long enough, that random walk, as we sort of move the blocks around in these little ways, okay, will converge to a high probability sample of a likely explanation. It's a very good way to do causal inference. It's just a very slow way. Okay? It's so slow, I'm not even going to bother to show you how slow it is. Okay. Some of you might be familiar with a famous idea in psychology from the psychologist Daniel Kahneman, thinking fast and slow, the idea that the brain has different kinds of systems for inference, some of which are fast and more reflexive, and others are slower, more reflective. The slower ones might be smarter and maybe more general, but also just take a long time. Okay. So we also have the same kind of idea when it comes to doing inference in probabilistic programs. A method like Markov chain Monte Carlo is a kind of thinking slow method. There are thinking fast methods that are actually based on neural networks, where you train the neural network by drawing forward samples. Instead of the reverse direction, you imagine scenes and then run graphics forward and see what they look like. And that gives you pairs of scene and image, and you get lots of those. You might get many thousands or millions of them. Scene, image, scene, image, scene, image. And that's the training data for one of these neural network or pattern recognition systems, which then learns to take a new image, and as long as it's not that different from ones that you've imagined before, can work backwards to make a good posterior guess very quickly. Okay. But it's less flexible, and if I show you scenes that go beyond the scenes you've previously seen or imagined, then it may not work as well. So you have trade-offs in these different systems, and again, some of the most robust inference combines them. Maybe you initialize with a guess from your bottom-up neural network, and then you do a little bit of top-down inference to try to refine it, for instance. So that's what's going on under the hood in the perception part. Now, what about the physics part, right? Because that just tells me what's out there. I want to know what's going to happen. Will this stack of blocks fall over, or how likely is it to fall, or how many will fall? And here, this is really quite simple. What we do is because the output of our perception system, this 3D object configuration, is the same kind of thing as the state of the physics engine. So these game physics engines run also on a description of 3D object shapes with adding in a few physical parameters like mass, friction coefficients, and elasticity, which can also be inferred using the same combination of top-down and bottom-up mechanisms. So you make a guess at what objects are there, their shapes, their basic physical parameters, and now you can just run your simulation engine forward and just sort of see what happens. So here's an example of one guess of one of these block towers and running a few steps of physics forward, and you can see that, well, most of the blocks fall. Here's another guess where the actual position of the blocks, or rather the inferred position of the blocks, is a little bit different. There's a little bit of uncertainty. And so when you run that state forward through the physics engine, the precise thing that happens is also rather different. But for the purposes of intuitive physics, it's basically the same, namely most of the blocks fell or moved. So all your system has to do is make a few guesses of that sort, run them a few time steps forward in physics, count up the results, and that's your guess. And when we do that sort of thing, we have a very nice model of this particular judgment of intuitive physics. So what I'm showing on the left is a plot of data from an experiment. Thank you. The y-axis is the average judgments of a group of human participants. They rate on a scale of 1 to 7 how stable or unstable is one of these block towers. And then on the x-axis is the average of a few simulations in this probabilistic approximate physics engine. And you can see there's a very nice correlation. You can see that here I'm showing 3 particular tower stimuli and their corresponding points. And over here on the right, I'm just contrasting with a model that is a very similar model, except without the probability, without the uncertainty. This is the same physics engine, but it knows exactly where the blocks are. And what you can see is that it's going to be more accurate in a ground truth sense, but it's actually a much less good model of people. The correlation with human judgments, again, on the y-axis and the model on the x-axis is less good. And you see some notable outliers, like this red point here, which is actually a kind of a stability illusion or a physics illusion. This is a configuration that is actually stable. So the ground truth physics says there's no chance that any of that's going to fall, and that's because it's just perfectly but precariously balanced. But people see that red tower as very unstable, right? That's why it's very high on the y-axis. And that's because, according to this model, because of the probabilistic part. Because while the actual position of the blocks are balanced, if you're not sure where they are, all the near neighbors of the actual ground truth ones, all the plausible good guesses, are actually unstable. And that's what you're seeing. Okay. Now, we could build different kinds of models. Like, for example, we could take a pattern recognition or neural network approach and train that system end to end, as they say, from images to labeled data on whether the thing falls or not. This is an example of a nice version of that, a network called FizzNet, produced just a few blocks from here, well, maybe a mile or so, at Facebook AI Research. And if you train this thing on enough data, like 200,000 images of this sort, of let's say 2, 3, or 4 cubes, then it can do very well. In fact, it can do nearly perfectly and a lot better than humans at predicting whether another stack of 2, 3, or 4 cubes is going to fall over. But that's a huge amount of training data just for a couple of cubes. And it doesn't generalize very much. Maybe it generalizes to 5 cubes, but it doesn't generalize to 10 blocks in all sorts of different shapes or blocks that aren't even cuboidal, let alone all sorts of other judgments that aren't just about, will this stack fall? Whereas the models that we've talked about here, because of these very general simulation tools, they can answer many different questions. Not just like, will this stack of blocks fall, but which way will they fall, how far will they fall, what happens, how will it change if, let's say, there's 2 different colors of blocks, and one color is 10 times heavier than the other. Notice this matched pair here, where the geometry of the blocks is the same, but we've just recolored them. And if you think of the gray stuff as 10 times heavier than the green stuff, you'll make a very different prediction about which way the blocks will fall. And our models do the same. Or seeing blocks like these ones, which look like they should be falling over, can you make a guess at whether the red or the yellow material is a lot heavier than the other, which might explain why they're not falling? Now, let me show you just one more intuitive physics demo, a different kind of task that the same models can apply to, which is importantly different than these ones here. These ones here, especially tasks like will the stack of blocks fall over, are ones that you have been making for many years. If you like to play with blocks as a kid, you've been maybe making these kinds of judgments for decades. And in that sense, they are the kind of task that you could build a pattern recognition system for. But maybe the most severe test of the kind of approach that we're talking about, which isn't based on pattern recognition, it's based on reasoning and simulation and probabilistic inference, is to take a task that, until I show you in a second, or unless you've maybe seen this talk, you've never seen before. Okay. But I can explain this task to you in English, and you can imagine what's going on in your minds and answer the questions very much like you would answer these other questions, and do almost as well. So here's the task or a question. Imagine if this table is bumped hard enough to knock some of the blocks onto the floor. Is it more likely to be red blocks or yellow blocks? So you guys tell me, red or yellow? Red. Obviously. Yeah, how about this one? Yellow. Everybody else, join in too. Bump. Okay. They're all obvious, right? No. Well, some of them are more obvious than others, right? Some of them feel a little quicker and clearer, right? That's another sign of probabilistic inference. But in some sense, these are intuitive, right? You didn't do detailed calculations, I assume. Some of you, maybe the mathematical geniuses there, the real geniuses, might have been able to do the calculations, but no, probably none of you could. All right, and yet somehow there is some engine in your brain which was able to make the right guesses. So how does that work? Well, here's a little glimpse inside one of these game physics engines. So what we imagine as scientists goes on inside your head when you answer this question is you reconstruct some kind of 3D model of the scene like this, and then you simulate a bump like this. Here's a little bump of the table. Here's another bump of the same table. The first one was very light, and this one is somewhat harder. And you can see that different things happen. When you give it a big force, the blocks move a lot more. Okay? But at the level of intuitive physics, at the level of the question I'm asking you, it's the same. Namely, all of the yellow blocks go over and few or none of the red blocks. So it didn't matter which of these samples you imagined. It also doesn't matter whether you run a detailed long-time simulation, which would be very costly and almost surely you don't do, or just a few steps of a much coarser approximate one. So think of it, I run this simulation for just a few time steps. You kind of already know what's going to happen. Same here, right? You don't have to run it all the way to the end. You don't have to track the positions very precisely. You just have to do a few short coarse simulations. And it turns out that that's enough to provide a mathematical model of people's judgments in this task. Again, I'm showing things in the same form with average human judgments on the vertical axis and the average of a few model simulations on the x-axis. And you can see that the correlation is almost as good as in the just will the blocks fall, right? It's not quite as good, but it's almost as good. But yet these, again, are so different. It's the same underlying physics, but while the first question is one that you might have done many, many times in your life, until tonight, perhaps, you never did this judgment. Yet you have in your head the ability to do it just as much as those things that were much more practiced, okay? So what we're talking about here, again, are systems for common sense, inference, and perception that don't do any learning. It's not to say that there isn't learning, and I'm going to spend the last part of the talk talking about learning, okay? But the point is that you, as adults, or even older children, where I guess we're all older children of various ages here at the Museum of Math especially, but you know, you've done, the intuitive physics in your head is the result of billions of years of evolution and years of learning over your early days, and maybe some other things too. But you come in here with a very powerful general purpose common sense machine in your head, okay? It doesn't have to be trained to do any new specific task. Rather, I can explain the task in English, and then you can just set it up and imagine what to do, okay? Now, to shift over for just a moment into AI, these same kinds of tools for intuitive physics are now being used by roboticists in a number of different areas. So I said we don't have any robots with the common sense intelligence in the physical world of young kids, but we're making little small steps. So these are all examples of projects that were not done in our group, but we collaborated with roboticists, using intuitive physics to build robots that could actually play the game Jenga, which was the inspiration for those block towers I showed you before, but also stack up blocks in all sorts of other ways. This is especially interesting here. This is the work of Marc Toussaint, using intuitive physics to allow a robot in a simulation to imagine how to use tools, including new tools that it's never encountered before. Some of you might have seen the remarkable tool-using abilities, not just of humans, but of other primates or crows or other smart tool-using birds. And roboticists have been very interested in how to get a robot to imagine, for example, how it could use a hook to get another bigger hook to get another object. And this is one of the first systems that can do that. Or in more sort of soft body systems that simulate kind of muscles, even using intuitive physics to learn to walk very quickly, much like the way humans seem like they take a while to walk, but many other animals, and even humans under the right circumstances, you know, think about the gazelle who pops out of the mother and then has to walk across the savannah within 10 or 15 minutes before the lion eats them, right? We and others have hypothesized that that's because you have something like a physics engine in your head, in the motor parts of your head, the action planning parts, which can be quickly tuned to learn to walk as well as to learn to manipulate other objects like this. Now, so that's intuitive physics. That's mostly what I was going to talk about in terms of the common sense side. I'll just point to the way, since I showed you that video of intuitive psychology, just some of the ways that we can use the same kinds of tools to capture some aspects of how we see other people's actions in the physical world and try to infer what they are trying to do. So here's just one demo where you'll see this woman in a slow motion a little bit reaching for one of the 16 objects in this 4x4 array on the table. And you try to guess which object is she reaching for. Okay. Just raise your hand when you think you know which one she's reaching for. You watch the video, I'll watch you. Okay, most of the hands have just gone up right around there. Okay. Now I wasn't watching the video, I was just watching you. But then I quickly looked back, and I think you saw what I saw, which is most of your hands went up. There were a few early deciders, but most of the hands went up right when this dashed line went up here, right? Did you see that? Okay, so this is not data from an experiment with people. This is model predictions, which, at least in some form, were somewhat verified by our little demonstration here. What these lines represent are the Bayesian posterior probabilities for each of the 16 hypotheses of which object she was reaching for. How do we compute those? Well, we have a forward causal model, a planning model, that says people plan their actions to efficiently achieve their goals given their beliefs of the world. What does efficiency mean? Well, it means something like maximizing the trade-off of rewards and cost. The reward is what you get for getting your goal object, and the cost is just how much you have to move, the energy in your muscles, let's say, okay, or the force that you have to exert. And there are tools, they're actually physics engines, that people in robotics use to compute the cost of an action for a complex humanoid or other kind of robotic body. We can use those tools to figure out the cost of a plan and to find the most cost-effective movement plan to achieve any one of these goals. And then we can work backwards to say which goal best explains what we actually saw, because which of the hypothesized plans is closest to what we actually see the person doing. And that's what I'm plotting here. That's the top-down or slow style of thinking. And we can also train neural networks with this as the underlying model to achieve a faster bottom-up style. And again, the actual models that we're trying to build here, this is kind of work in progress, combine that bottom-up and top-down style of inference. And this is just the beginning, of course. We're not just interested in reaching, but all the more complex ways that one or multiple people might interact in more flexible ways in the world, like you saw. I'm going to just skip through a little bit of other stuff on ways we can do intuitive psychology, but I'm happy to talk more about that if you're interested. And I want to spend the last couple of minutes, well, couple meaning more like 10, talking about studies with young children and learning. So we've used these models together with colleagues who do infant research to build some of the first quantitative mathematical models of infant common sense. So for example, with 12-month-olds, you can study their intuitive physics by showing them, I want my video to play here. By showing them this little gumball machine. This is work from Luca Bonatti's lab by Erno Teglas and colleagues, where these objects bounce around inside this thing. There's a period of occlusion, and then after some time, 1 or 2 seconds, an object appears. And you can vary the color of the object, whether it was one of the rare or common ones, which objects were close to the exit when at the point of occlusion, how long the occlusion was. And all of those factors make a difference in what you expect, which color object you expect to emerge. Infants, this is the sort of classic infant method to understand their expectations, just like you. When I show you something surprising, if you go to a magic show, somebody shows you something surprising and you look at it longer. So infants look longer when they see things that violate their expectations. And here we're able to quantitatively predict infants' looking time based on how surprising it is, or the inverse probability, 1 minus the probability, under one of these intuitive physics models. Here's an example in intuitive psychology where you'll see, again, an agent reaching for a goal, but in a somewhat unusual way. This agent is going to jump over a wall. Well, that was a wall that it didn't jump over, but now the agent sees another object, and it does jump over the wall. And in these studies, which were done by Sherry Liu and Tomer Ullman in Liz Spelke's lab, infants see a series of scenes like this, where one agent, and this agent isn't a human body, it's like a little ball with some eyes, is presented with one possible goal that it might jump over a barrier to, and then another possible goal. And on different trials, it either does or doesn't take this action. And the key is that the actions vary in cost. So the cost could be the height of the wall it has to jump over, so how high is the jump? Or a number of other physical variables, like there could be a ramp, and by varying the steepness of the ramp that the agent has to go up to get to its goal, that imposes a cost. Or there could be a gap the agent has to jump across, and we vary the width of the gap. And the key is that infants, these are only 10-month-olds, they look at the pattern of actions that the agent takes or doesn't take and their relative costs, and use that to work backwards to understand how much the infant likes or doesn't like different objects. The more the agent is willing to pay a cost to take a more costly action, the more the infants think that the agent likes that thing. So in this case, it's the yellow thing more than the blue thing. Okay, and we can model that mathematically with a model that uses physics to compute the cost and then works backwards to, again, infer the most likely reward values. So these are just a couple examples of how we're actually able to capture mathematically some of the ways that even young infants understand the world in physics and psychology. Now, where does learning come into the picture? Well, this is, in some sense, the most interesting question. And it's a hard question. Nobody has the answer to this. One route that is being pursued by a number of researchers in AI is, it represents the in the classic nature versus nurture, or empiricism, if you like, versus nativism debates, there's a long history of philosophers and psychologists arguing back and forth about how much of knowledge is built into our brains innately, let's say as Plato or Kant suggested, or how much is just learned from experience. A lot of machine learning and AI research, especially with neural networks, which are very general learning tools, has suggested that maybe we can just build gigantic neural networks like the physics network I showed you, okay, and learn these things. And there's some interesting work, especially by DeepMind, the AI company which very famous for producing AlphaGo, the machine that beat the world's best Go player, and other systems, where they take some of the same kinds of things I've shown you here and try to build neural networks that can capture this common sense knowledge of infants. And I'd say there's some interesting things about these models, but they have the same problem as the other pure neural network systems I showed before, which is you can train them on a big training data set, but they don't really generalize beyond that to new situations, and especially to new tasks, as you've seen our common sense is able to. So the approach we take is one where we start off building in a lot of structure, something like a game engine. But just as if you're designing a video game, the game engine is just the starting point, right? Game engine's not a video game. It's just the software architecture and the resources that allow you to make a game, and actually to make an endless variety of games, all the different games somebody could imagine. And the game industry is thriving, and there's, no end in sight for the games that people can come up with. So here we think of, analogously, sort of learning as learning in the game engine, learning the game engine itself, and then building on that to learn all the things that go beyond just these basic aspects of common sense, like things you get from language that sits on top of what you have in the game engine, and then all that culture gives you. This is mostly work in progress that we're doing, but just to give you a little taste of it, I'll show you the kind of thing that we're trying to do here. So the idea is, again, we have the game engine, and you're trying to sort of learn the game engine of your life. We're very much inspired by work that infant researchers, like, for example, I've mentioned Spelke a number of times, or here this is a slide from work by René Baerjahn, another one of the great psychologists who studied infant intuitive physics, where you can actually, study, and take everything that I say here with big error bars and grains of salt, but you can identify very, very roughly something of the learning trajectory that infants go through in the first few months of life, in terms of what they understand from the earliest ages and what they come to understand with a few months more experience. And that's useful data for us. It sets the kind of architecture, it sets the roadmap and the landscape for learning. So our goal here is to try to capture the different stages of knowledge in, let's say, intuitive physics as different stages in the development, building out or growing out of one of these game physics engines. And then we want to build learning algorithms which can explain how, with a rich experience, but not that much experience compared to like a big data machine learning system, how you can go from the earlier stages to the later stages. Okay. So the input is experience, and the output is let's say, an intuitive physics engine. Now, this is a hard problem of learning. We like to call it the hard problem of learning. Cognitive scientists love dubbing various things the hard problem of X or Y. By saying that it's the hard problem of learning, what I mean is, compared to learning in a neural network, it's a lot harder. So this is a picture of the thing I was describing in words before, this continuous error landscape, which underlies any end-to-end differentiable system, like a big neural network, where you can, at any point in this space, compute the slope of the surface, the direction of steepest descent, and neural net learning algorithms compute that slope, and then they roll downhill. And it turns out, if you're willing to wait long enough, then rolling downhill finds the bottom. Okay, you have to be a little clever. It's the so-called stochastic gradient descent that avoids getting stuck in local minima, but that's basically what happens. Okay, whereas if you're thinking about building a game engine program, what we're talking about effectively is a program learning program, right? A learning algorithm whose output are the algorithms that simulate physics. So we're talking about search now not in neural network weight space, but in the space of programs. And this doesn't have anything like a nice topology or geometry that learning in the space of neural networks does. So it's a much harder problem. Now, we've made a couple of small steps towards this solution. One is work that Brendan Lake, my colleague who's now at NYU and one of Molly's colleagues, did as part of his PhD thesis, where he built a system to learn very simple programs that capture the visual concepts of these handwritten characters. So this is far from learning a game engine. But what you see here are basically very simple visual concepts, characters in many of the world's alphabets, which you can learn from just one example each, right? A machine learning system for computer vision or character recognition typically requires hundreds or thousands of examples of any one character to be able to recognize new instances. But here, even for alphabets that you've never seen before, you can identify each and every one of these as its own thing, right? And then recognize other instances or even imagine other instances. So we built a system that we call Bayesian program learning, which captures the way people draw, the way we write and the way we draw, with a series of probabilistic programs. It's a hierarchical probabilistic program. It's a causal model of the sort we're talking about. But the program is now a drawing or action program. And then we can use the Bayesian inference machinery in probabilistic programs to run these programs backwards to see the output of one of these drawing programs, which is one of these new characters, and infer backwards what was the underlying patterns of strokes and substrokes, the action program that led to what we saw. That allows us now to it gives us a model we can fit to other instances, and we can even use it to imagine, in a very limited way, to imagine some new things. So the system that we built here passed a very simple kind of visual Turing test, which I can illustrate for you here. We asked our system, as well as 9 people, to imagine new instances of a character. So we gave them the one character you see on the top, and then we asked our system to imagine 9 other instances of that same concept, and we asked 9 people to do the same. One each. And then we asked other people, like I'm going to ask you here, can you tell the difference? Can you see which of these were imagined by the person, or the people, and which by the machine? So what do you think? Can you tell? Think about it for a moment. I'll show you the answer. It's different in each case. Left or right, think about it. Okay, here's the answer. Those are the machine. Anybody get them all right? Yes. Really? Okay, good. We'll test you in a second. Probably most of you, I guess, got about 3 of them right. Most people are just at chance. Okay, now here's your chance. Let's test again. Okay, see if you can tell which is which. Yeah, do you think you can tell now? Were you right? Maybe?
I got the top left because that was the only one that I looked at.
Oh, well, okay, you might have gotten them right. I've met exactly 1.5 people who have been able to tell. Maybe now 2.5. And I won't talk about why some people might be able to tell or not. But most people are at chance. Okay, so our system is passing a very simple version of the Turing test, which means it's captured something of the human level ability to grasp a concept from one example. Now this is just a very small step, but it does scale somewhat. So the same kinds of ideas are currently being used to learn not just handwritten characters, but spoken words or other kinds of cultural symbol systems, like dances or gestures, to learn about tools, to learn programs that describe 3D shapes. Okay? And going forward, where we see the field going is a much richer view of, let's call it, learning as programming. This is the slogan that I mentioned, what you could call the child as coder or the child as hacker. The idea, so of course, probably most of you know, at MIT, hacking is a good thing, and the rest of the world, hacking is a bad thing. But at MIT, hacking is coding in a particularly creative, playful way. All right, but the idea that if our basic common sense knowledge is programs or systems of programs, then learning is something like programming, and we think of this gives us a perspective on both the goals and the mechanisms of learning. Learning isn't just making your code more accurate, but as we say when we're hacking, making your code more awesome. That could mean more accurate, but it could mean faster, or more efficient, or more elegant, or more reusable, or more explainable, or just more clever, okay? And children in their learning and their thinking are interested in all of those things. So it's a much richer picture of the goals of learning, but also of the mechanisms of learning. So think about all the ways you make your code more awesome. Well, one way to do it is to have a fixed piece of code with some parameters that govern its performance and tune those parameters to optimize for some metric. That's what you do when you're learning in neural networks, and it's one way to improve your code. But think about all the other things you do that don't just involve tuning the parameters of existing functions. All the ways, for example, that you can extend or write new functions, that you can debug existing functions, you can write whole new libraries of code, or even new programming languages. Okay? And we think human learning has analogs to all of these. If we want to capture how children find structure in the world, if you like the child as scientist idea, the algorithmic version of that is something like writing new programming languages. So we've recently made another small step towards this, and this is the very last thing I'll tell you about, and then we'll wrap up and maybe take a couple of questions, is we've built a system that we call Dreamcoder, because it learns in its sleep, kind of like you. And what it does is it learns to solve many different problems in different domains, in each case by writing code. But the key is that it learns to learn because it learns whole new programming languages. Every one of its programming languages is written in Lisp, so I promised you Lisp while old is back again. Here, what the system does is, for example, it might start off with a very primitive set, or a very basic set of functional programming primitives, and then it might take a problem like, for example, given lists of numbers, it wants to learn to sort the lists from the input to a sorted output set. And it does that by writing code in a library of functions that it progressively over time synthesizes starting from the initial state. So here, for example, over multiple iterations, it learns a filter function, it learns a maximum function, it learns a nth largest element function, which it can then put together into code like this, a very short, simple program that sorts a list. Okay, this system was not able to learn how to sort lists when it started, because if you were to write that sorting program in the original code, it's incredibly long and you'd never be able to find it. But by learning over time and learning to write your own language of code, you become able to find short, simple, elegant, explainable solutions to a range of problems in this domain and many others. And I don't have time, or I'm sure you don't have time at this point either, for me to try to tell you the details of what we mean by dream learning. But just as you do, when you're in your sleep, the scientists have distinguished different phases of sleep, which nobody really knows what they're for, but there's many interesting hypotheses that involve things like abstraction and compression, as well as practice and rehearsal. And this system involves both of those, where the new programming language functions come from a process of abstracting out common elements in existing solutions. And we can give it, for example, problems of drawing or building, like I'm sure many of you are familiar with the programming language Logo. And we start off with a version of Logo where you can just put your pen down and move it and turn. That's the turtle graphics. But the system then learns new functions, like for drawing semicircles, circles, spirals, polygons, or higher order functions like radial symmetry, where you take a basic element and you repeat it sometimes radially. These are its dreams, which I think show you something about what's going on here. At the beginning, the dreams are just random samples of programs. Remember how we said you can train neural networks to do approximate inference? So that's what's going on here. There's a symbolic language that's being built out, and then in your dreaming, you're imagining making up new problems to solve to train your neural network to guide the search. And at the early stages of learning, on the left there, the dreams aren't very interesting. But by the time you've become an expert in this domain, you can imagine all sorts of crazy things that then show the advancing expertise. And this kind of system can learn some of the basics of functional programming, or even here we gave it a set of basically problems that came from AP Physics, starting off with a basic set of functional programming and very basic arithmetic operations, and it learns kind of a language of vector algebra, and then it learns actually languages of mechanics and electricity. So it can learn to express programs for Coulomb's law or Newton's law. So maybe even learning a little bit of mathematics. All right. So to wrap up then, I've tried to show you a vision for how we can reverse engineer the earliest stages of common sense, as well as how we go beyond this, how we learned new languages of thought that sit on top of our intuitive physics and our intuitive psychology, starting with natural language like English, but then building formal languages like logic or math or computer programming that together put all those tools together, help us go beyond our common sense to access the full sweep of human knowledge that builds culturally across generations and across cultures. And maybe, looking forward, will help us fulfill AI's greatest dream, to build a machine that actually grows into intelligence the way a person does. And what I've tried to show you here are some of the lessons and insights that build on developmental psychology of the past few decades, all the ways that we've learned that children are smarter than just starting off as a blank slate and learning by just finding patterns in big data, and ways we've been trying to capture these with engineering tools like probabilistic programs, program induction, game engine programs, and so on. It's still very early stages, but I hope you've gotten a taste for why I'm so excited about this, and if any of you are interested in this, I'd love to talk with you more about it. Thank you.
All right, we have time for a couple of questions. You can raise your hand. I will bring the microphone to you.
Thank you very much for a beautiful presentation. I have a question regarding conscious, whether it's a form of, elevated form of intelligence. If so, are we racing to get into an artificial conscious?
That's a very fundamental question. And I'm not, so you said, I mean, there's a number of things you might be asking. I guess part of what you're asking is, are you asking where does consciousness come into this picture? Or
More specifically, like the artificial intelligence, if it is a model that replicates the human intelligence,
yes.
and when you look at let's say the animal kingdom, and then you can sort of sort the intelligence from the lower to the higher, at some point there is the recognition of self.
Yes, right.
That exists at some place in this.
Yes. So this is a topic that I haven't worked on very much, but I've actually started to work on. I gave a version of this talk in a conference organized by Stan DeHaan, who's a leading cognitive scientist. He works on the cognitive science of mathematics, but he also works on consciousness. And I didn't think I was working on consciousness until he told me after the talk that I was. He said, you know, I think that your model, the stuff I talked about here, could be a way to describe in engineering terms his theory of consciousness. And we talked for a while, and that actually inspired me to start thinking about it more seriously. I think the connection, and again, this is not to say this is a model of consciousness or this is going to lead to conscious machines, but it might be going in this direction. Remember, we started off by saying that the essence, or one of the essential features of human intelligence is the ability to model the world, not just to recognize patterns in data, but to model the world. So one of the things in the world to model is us, right? And you talk about the self, and I think many people, such as DeHaan and others, would say that consciousness starts with an organism that has not only a model of the world, but a model of itself in the world, and how the world appears to it, right? And all I can say is that we're starting to think about this. We've been working with some other cognitive scientists and some philosophers, for example, the philosopher Laurie Paul, who we've started collaborating with, and we've been working on a project that we call reverse engineering the self, where we try to take these tools and sort of build up minimal components for describing what it would be to have an intelligence that has a model of itself and that uses that in important functional ways to structure its own learning and thinking. Will that actually lead to a full theory of consciousness? You know, I don't think it addresses the hard problem of consciousness, but it addresses some of the interesting ones that are also relevant to building AI.
Professor, may I ask you such a question about the ultimate dream goal to build a machine that will grow intelligence the way a human being does?
Yes.
Can you share your thoughts? So at the ultimate time, do we want to build our helpers or somebody who will eventually conquer humans, and that will be the end of humanity on this planet? Thank you.
So, I'll tell you my view, but of course it's not up to me, it's up to all of us. So my view is that there's a lot of value in the short term and the long term for trying to understand human intelligence in engineering terms and engineer more human-like forms of AI using what we learn. But that doesn't mean that our goal is to build an artificial human, right? It doesn't mean that we're trying to completely replicate everything that we learn about humans in machines. There's all sorts of reasons why we wouldn't want to do that. But as we know, right, I mean, think about the way it works in biology, where as we achieve more and more of an understanding of how biology works in systems kind of thinking and engineering terms, we can then hopefully design better drugs or other kind of therapies, or we might design various forms of synthetic biology. But when you have an engineering understanding, you have a toolkit, and you can build new things with some of those tools, but not others, right? So what we hope, for example, is that we could use these ideas to build machines that are smart in some human-like ways, but maybe not in others, right? Or that are human-like in some forms, but maybe not others. So we might want systems, for example, that we could have a conversation with, that we could talk to, teach, and maybe in some form, importantly, trust the way we might do with each other, right? I mean, at the heart of human intelligence is a certain way to interact with people who we've never met before, but we can still exchange words, understand each other, and hopefully trust each other. And we could build potentially machines that do the same thing. At the same time, these machines wouldn't necessarily have other human properties, which are the ability, for example, to arbitrarily set certain kinds of goals for yourself, like the goal to take over the world. So we might have to be smart about how we engineer the goals of these systems, and that could be independent of how we engineer, for example, their ability to understand an agent with goals, right? And then to render that into language. So what I hope is that we will use these tools, and again, it's not up to me, it's up to all of us. You know, I could stop working or die tomorrow, I hope not, but these days the world presents many uncertainties to us, and it wouldn't matter for anything like AI. You know, there's lots of people are working on AI, and there's all sorts of incentives for people to build smarter and more human-like forms of intelligence. So it's up to us to try to understand what are the possibilities and to try to make smart choices about how we build things. But I think the more we build AI that follows science, the more we'll understand it. And what we will avoid are dangers, for example, of building systems that we don't understand, that might do things that we don't predict. You know, engineering has always been about building things. Think about how we engineer airplanes, at least most of the time, right? Or how we engineer computer systems. We build things that we understand, right, based on fundamental science, whether it's aerodynamics or material science or information theory or computation, and then we use them to do things that we want as individuals and collectively. So AI shouldn't be any different.
Oh,
Sorry. Oh, yeah, go ahead.
Thank you, Professor. I'm interested in the philosophy and the phenomenon of intelligence. And this is
Me too.
related to the first question, which is about being in the world, which is kind of one's orientation in the world. But I'm interested in a more concrete existence, which is, in the case of human, is bodily existence.
Yeah.
And for humans, the intaking information is through all various kinds of senses in the body, and that our way of orienting ourselves around the world is different from the way machines take in this input, which are in the form of numbers. And I wonder whether engineering intelligence in the future would involve, in some way, expanding the input from just this mathematized input into building more sense mechanisms that simulate human.
Yeah, I mean, I think that's a good question, but in some form, we're already well on the way to that, and you know, if you look in the field of robotics, right? So, and to some extent, it kind of the field of robotics would not draw the same distinction that you would draw between having a body and experiencing the world through your body and experiencing the world through numbers. Because what you do in robots is you build bodies. They're definitely bodies. And they have senses like vision, but also touch, right? And other sense of their proprioception. And they experience the world through those senses, and they are intelligent in a way that's grounded and acts on the world. But they also transduce the bodily sensations into numbers that the computation inside the robot's brain can process. And neuroscientists would say, well, your brain does the same thing, right? We can take the nerve impulses from your senses, your sense of touch, right? Or your eyes or your ears, and also turn them into numbers. And the kinds of models that we're talking about, when we apply them in the context of the brain, describe how common sense can come from processing those numbers. So I don't think there's a conflict between those. And I think, but you're pointing to the very real importance, I think, of AI that doesn't just live in a world of pure numbers, right? Like the internet or the world of finance, where a lot of machine learning is practiced, but actually lives in the human world with something like a human sort of interface. And that's certainly our goal on the AI side, is to build AI that lives in the human world, that humans can interact with the way we've always interacted with each other, right? Some people, I mean, maybe this goes also to your question, you could imagine a future of AI where we live in the AI's world, but I would prefer a future where the AI lives in our world, right? And so that means thinking about how to design AI that, like humans, is designed to live and function successfully in a human world with other humans. That starts with the body, but it goes well beyond the body. But that's the direction that we're pointing towards.
Hello, thank you very much for your talk. I was wondering, what do you think about this idea that there is one learning algorithm hypothesis, and that basically the brain uses basically this algorithm to understand the different input modalities. And also I was wondering, how does that relate to the universal approximation theorem?
Which universal approximation theorem?
The one for the neural networks, that with only one layer you can approximate basically any function.
Okay. So, yes, so there's a long history of interest in having like a single learning mechanism that could explain the origin of all intelligence in brains, minds, and machines, right? And it is related to some interesting theory in mathematics of universal approximation. Now, this idea has taken on many different forms. And you know, if you had asked me a few years ago, what do I think of that? Well, if you'd asked me 20 years ago, I would have said, yeah, I'm interested in that. I think that might be right. And I think the universal learning algorithm is Bayes' rule. You saw me talk a lot about Bayesian inference. And in some sense, I still think that's true. I just think it doesn't do very much work for you. So many of you might have read the Feynman lectures in physics. Right? Have you read that? Do you remember the part towards the end where he says everybody wants there to be one equation that encapsulates all physics in one simple equation? And he says, well, sure enough, here it is. U equals 0. And he puts a box around it. What is U? U is unphysicalness. Right? And that's kind of how I feel about simple general learning rules. Bayes' theorem is, I think, more useful than U equals 0. But it's really just, it's just one part. In a sense, it expresses consistency conditions on any kind of learning algorithm. Now, when people talk about universal learning in neural network, it's true that a neural network, as well as many other kinds of learnable function approximators, can be said to be universal approximators. And here, the math that they're drawing on is analysis, real analysis and functional analysis, where you talk about functions that are functions, you know, from, let's say, Rn to Rm or something, and you want to say, well, any task can be conceived of as a function from some high-dimensional space to some other high-dimensional space, and we want to show that if you get enough examples from this, you can approximate that function arbitrarily well. Personally, I don't think that's the answer to intelligence because, as I tried to say at the beginning, I don't think intelligence is just about function approximation. Rather, it's about model building and then using those models to set with goals that we set to solve problems, as I talked about here. But I would say that in the last few years, I've come back to the idea of thinking about, if not universal, at least very broad kinds of learning algorithms, like the thing I showed you at the end, this thing we call dreamcoder, which learns these libraries of symbolic functions. In some sense, that is something like a kind of universal learner, but not in terms of a neural network, rather in terms of symbolic code. And the universality there isn't from functional analysis, but it comes from algebra and logic, namely the universality of the lambda calculus as a expression of any possible computation, right? Like a Turing machine, but in algebraic form. And that's what we're doing here, is that we're taking advantage of that to learn code that could express any function. And then there are analogous kinds of universal approximation, which comes from things like Kolmogorov complexity, if people are familiar with that. And in some form, you could see what we're doing in this is an algorithmic, practical approach to trying to basically universally learn universal approximations to some underlying code. Now, do I think that's going to be the answer to all of intelligence? No. But I do think that it expresses, at least in some form, something of the human ability to go beyond that initial common sense language that we start off with, which looks something like a game engine, and to be able to learn not just new functions, but whole new programming languages, or what cognitive scientists and philosophers sometimes call languages of thought. All right, which allow me to think about things that I wasn't equipped from evolution to do, but which I can get from experience culturally with the kinds of experiences that we have in our modern world. And I think the real singularity, if you like, when people talk about universal learning, it also connects with notions of singularity and intelligence that can understand itself and bootstrap. For human intelligence, the real singularity doesn't come at 18 months. It comes a little bit later once you actually learn language, first a natural language, and then use that, like English, and then use that to learn these formal languages, whether it's math or programming languages and so on, that then allows you to learn all these things that you never experienced, but that you get from the accumulated wisdom of of all of human culture, right? Which transmits across generations and across culture through those languages. That's the real singularity of human intelligence. And again, I think we have to hope that if we build AI that goes in that direction, that it goes in a positive direction. And that, again, that's up to us, what kind of experiences, what kind of languages, what kind of cultures we grow together. Okay, I think that's a good place. Well, I'm happy to take one more question if there's time, but I'm happy. Okay, go ahead. Yeah. Sure. Oh, yeah, definitely. Yeah.
Yeah, I'm not an expert, really.
None of us are.
Yeah. Like, couldn't you just like make it like scan situations and then like get a program for that? Like, how it write a program for itself, like about the situation that it sees?
So build a machine that scans situations and write its own programs to describe what it sees.
Yeah.
Yeah, that's it. I think that's a good description of what I was just talking about. I mean, I like that idea, but to actually do that, to write a program that can write its own programs is pretty hard, right? But we've made some small steps towards that with the things that I talked about at the end, and they're potentially quite general purpose tools for doing that. It's amazing. I mean, this is one of the neat things about working on AI as well as cognitive science, is that anybody, you don't have to be an expert to formulate what I think might be the right problems, and even to kind of come up with might be, common sense, basic ways to approach them. Actually making that work with mathematics and engineering isn't trivial, as the mathematicians like to say. But it's a project that we can all work on, and it's very exciting. I mean, it's one of, I'll just say, maybe it's a good way to close. When I was growing up in high school, I kind of wanted to be a mathematician. I had a great high school math teacher who exposed me to some early challenge problems, and I played around with things, and I spent lots of hours doing math research, which was not real math. It was kind of playing with patterns and numbers, actually. And it wasn't that long before I realized I wasn't going to be a great mathematician. That to really do real math research, I discovered something by finding patterns in numbers that turned out, I thought I had discovered a new theorem in number theory. I couldn't prove it, but I was almost sure of it by my computer simulations. It turned out Fermat had conjectured the same thing. I was like, scooped by Fermat. He couldn't prove it either, so that made me feel a little bit better. But it's so exciting that, any kid playing around with math might get to the level of Fermat, but that's hundreds of years ago. When you're working on intelligence, you can actually get right to the forefront of the field and do work that pushes our understanding of intelligence beyond where it's ever been before. And that's because of the unique opportunity that we have right now, which is we have tools, scientific tools and engineering tools that no humans have ever had before. So it's an incredibly exciting time to be doing this kind of mathematics. And I know many of you share that excitement, which is why you're here. So let's see where we go. And again, let's keep in mind how to make wise choices so that we build the right kinds of intelligence. Okay. Thanks very much.
Let's thank our speaker. And thank you all for coming.